Hello and welcome to Lecture 3 of Electric Current and Resistance in Phys 1201. In this lecture we're looking at Ohm's law, which takes the ideas that we developed in the last lecture and turns them into an equation that will be useful in circuit analysis. We've actually already seen Ohm's law. We saw it at the end of last lecture. It was this one. And remember that this applies to resistors and wires. Now, the way I'm writing it is not the usual way you'll see it. I'm writing it this way to stress that currents through resistors and wires are caused by potential differences. And so just like last term, I would tend to write A is a sum of forces divided by a mass, and write it that way because the acceleration is the thing that's caused by the forces. I'm now writing I is delta V across the resistor over the resistance because I want to stress that the current is the thing that's caused by the potential difference. So you'll more commonly see it written this way. And this is more practical for day-to-day use when you're actually manipulating it in equations. Note, it applies to resistors and wires. So it doesn't apply to all sorts of things that are called non-ohmic and which are just way more complicated. Diodes, transistors, a whole lot of other things. It doesn't apply to batteries, right? Batteries, the definition of the way a battery works is that it provides a constant potential difference. It does not depend on the current through the battery. That's actually an approximation, but as long as the current through the battery is low enough, it's a very good approximation. And the other thing it doesn't apply to that we've seen already is capacitors. We know how to calculate a potential difference across a capacitor, and it depends on the charge on the capacitor. It doesn't depend on the current. One more thing, while Ohm's law does apply to resistors and wires, usually we only use it for resistors. We don't typically use it for wires. For wires, we most often make what's called the ideal wire approximation, which is that the resistance of a wire is zero, which means if the resistance of a wire is zero, that the voltage drop across a wire is zero. And that's a good approximation as long as your wires are not too long or as long as they are connected to resistors that are large enough resistance that their resistance is much bigger than the resistance of the wires. Let's use some of these ideas that we've been talking about to talk about the simplest circuit of all. So here it is, a battery with a resistor. And we're going to make the ideal wire approximation that the wires have zero resistance, and so there's no potential difference across the wires. And this is a circuit diagram of this circuit. If you don't understand circuit diagrams yet, then don't worry about it. We'll talk about them in the next unit. All right, so I'm going to do the same thing we did with a battery and capacitor circuit and draw a potential versus position graph. So I've defined some locations, A, B, C, D, which I've indicated at points around the circuit. And I'm going to be totally arbitrary and say that the potential at A is 1 volt, right? I can make it anything I want because only potential differences matter. So I'm going to say 1 volt, and there is my potential at A. And now as we go forward through the battery, the potential rises by 1.5 volts. That is the production of potential energy, electrical potential energy from chemical potential energy in the battery. And now it doesn't change in the wire. That's the ideal wire approximation. And then between C and D, there's going to be a transformation from potential energy to thermal energy in the resistor. So the potential is going to drop, and it has to get back because when we return to A, we have to be back at what we started at, 1 volt, and so we'll see a 1.5 volt delta V in the resistor. All right, so now we can find something because remember the current, we don't know the current. We know it's the same everywhere. There's a current in here, there's a current here, and they've got to be the same, right? Think of the skiers going up the ski hill, they all come back down. And the battery doesn't determine the current. It's the battery in combination with the resistor that does. And we can now find it because we know that the current through the resistor is the potential difference across the resistor over the resistance of the resistor. And so that's just 1.5 volts over 300 ohms. And so that comes out to 0.005 amps or 5 milliamps. So we know that in a resistor, as charge flows through the resistor, it's losing electrical potential energy and it's turning it into thermal energy. And so let's look at the rate at which that happens, because a major concern when you're designing circuits is the rate at which they consume energy. So we know, let's have this resistor, it's a 30 ohm resistor, and let's say there's 2 amps of current running through it. Why? I don't know. Somewhere else there's a battery or something that's making current run through this resistor. I don't care about that right now. I just want to focus on this resistor with current running through it. Well, we know that there will be a voltage drop across the resistor because the charge's positive conventional current has a high potential energy here and a low potential energy here, and the potential is just the potential energy per unit charge, and so that is dropping. Let's see how much it drops in this resistor. So our potential difference across the resistor is just IR, and that's just 30 ohms times 2 amps. We know an ohm is a volt per amp, and so that is just 60 volts. So there's a 60 volt potential difference across this resistor, and so that tells us that it was 100 volts. I just arbitrarily said it was 100 volts over here at A, over here at B. Now it is 40 volts, right? 60 volts below what it was. Now let's look at the power usage, the rate at which UE is turning into thermal energy. Well, think about that. We have in 1 second, we've got 2 coulombs, right? That's what 2 amps is, 2 coulombs per second. So in 1 second, 2 coulombs flow through. As they pass point A, at A, the potential energy of that, well, it's going to be a Q times V, right? And so that is just 2 coulombs times our 100 volts, or 200 joules. And that's at A. At B, same thing. It's our 2 coulombs, but over here the potential is only 40 volts. And so 80 joules is the potential energy of that 2 coulombs of charge. And so we have a change in potential energy that is negative. I don't care about the sign. I know potential energy is being lost here, so I'm just going to be sloppy and say 120 joules. Well, our power is just the rate at which energy is transformed from one form to another. So a change in energy over a time it took. Well, this is easy. We've got 120 joules of energy transformed in 1 second. That's the easiest division in the world. 120 watts. There we go. That is the rate at which energy is being transformed in this resistor. And notice that all I used was the definition of potential there and the definition of power there. So I did that for a resistor, but notice that because all I used were these 2 definitions, and these 2 definitions are totally general, this will apply to anything. So it doesn't matter if I was talking about a battery instead, where there was some delta V across the battery and we knew the current through the battery. Once again, the power, we would say, in the battery, but that's kind of slang, right? This is the rate at which energy is being transformed from chemical potential energy to electrical potential, is again going to be I delta V. And for batteries, that's about the only way we ever have of calculating this. But now look, there's another way with a resistor. So come back up to our resistor and note, we know that the power, so this is for a battery, that's always the case. And you can do this for a resistor. If you know delta V and I. You can do that for a resistor. But you have another choice with a resistor, and this only works for a resistor. If you don't know both of those, sometimes you can do it another way, because the power is I delta V, but we know in a resistor that delta V is IR. And so I squared R is also the power in a resistor. That's another way of getting it. So if you don't know delta V across the resistor, that gives you a shortcut. But also, if you don't know the current, but let's say you do know the delta V, well, since delta V across the resistor is IR, then I through the resistor is delta VR over R. And so you can also write this as delta V over R times the delta V. Okay, I've just taken this expression again and resubstituted for I. And so that is delta V squared over R. And so you have these two different ways of calculating the power, the rate at which energy is transformed in a resistor. One which is good if you don't know the voltage, and the other which is good if you don't know the current. Let's come back to our simplest circuit here and talk about power. So we can calculate the power, what we would say, you'd often hear it described as the power in the battery. So remember, a power is a rate at which energy transformation is occurring. And in a battery, that is that we have chemical energy being transformed into electrical potential energy. And so this P-BAT, power in the battery, is talking about the rate at which that occurs. And it will simply be the current through the battery, which is I delta V bat. And so that is just our 0.005 amps times our 1.5 volts. And so that is just 0.0075. And we know an amp times a volt is a watt. We've already checked that. Or we could write that as 7.5 milliwatts. Let's double check now for the resistor. So we could calculate it actually the same way, but I'm going to make a point of doing it using this form. And so it is 0.005 amps squared times the resistance in this resistor, which was 300 ohms. And you can go ahead and throw that into a calculator. And lo and behold, it comes out to exactly the same value, 7.5 times 10 to the negative 3 watts, right? That's exactly what we found before. Note, that had to be true. These had to be equal because the battery is putting electrical potential energy into the circuit. And if that electrical potential energy built up in the circuit, this circuit would be getting more and more and more energetic. Well, that would mean if you left your battery running with this resistor, eventually you'd have a dangerous situation with a huge buildup of energy. No, all of the energy you put in with the battery is dissipated. It leaves the circuit by being turned into thermal energy in the resistor. And so you always find in resistor circuits that the power in at the batteries, the power in, which is generally at batteries, always equals the power out, or the power losses, which are usually in your resistors.